Swayam Prabha. Digital India. Educated India.
Dear students, we are back in the lecture series on course material of Transportation Engineering 2. In today's lecture, we will be discussing the aspects related to horizontal curve and super elevation. In the previous lecture, we have started with the geometric design, and we have looked at the different elements which we have to consider under the geometric design, and then we have specifically discussed the alignment of railways. Today's lecture is a continuation in that sense, and we will be today specifically discussing the horizontal curve and the provision of super elevation on horizontal curves. In this case, we will be discussing the radius and the degree of curve, the versine of curve, the measurement of degree of curve in the field, super elevation and derivation of equation for super elevation. The first 3 points are related to the horizontal curves, whereas the last 2 points they are related to the provision of super elevation on horizontal curves. Starting with the horizontal curves, first of all we define what is a curve. A curve is a required device which is required to change the direction of movement of any moving object. When we are talking about this change in direction in the plan, then it is termed as horizontal curve. It is required to join 2 gradients at the points they meet so as to provide a smooth movement over those 2 gradients, then it is termed as vertical curve. Now, as soon as we are talking about the gradients, it means we are discussing the vertical profile, and here we are in the vertical plane. So, because we are in the vertical plane, the connectivity of these 2 gradients are termed by the name vertical curves. Wherever the 2 straight portions have been joined together by some curvilinear portion, so that is a curve being provided at that location. And in whatever is the case, whether we are talking about horizontal curve or we are talking about the vertical curve, the change of direction is involved in that movement. In the case of curves, there are certain objections to the provision of curve. The objections are it prevents the use of heavy locomotive. The reason behind is that if there is a sharp curve being provided, then in that case the heavy locomotives have a difficulty to negotiate those sharp curves because of the rigid base of the locomotives, because they are bigger in size, and because of their bigger size there is a lesser flexibility in making an operation on any such type of a curve. Another problem which can be associated here is the possibility of derailment or overturning. As far as the horizontal curve, horizontal or straight section is being provided, the 2 things which are happening is the one is the longitudinal movement, and for some point of a time there is a lateral sway or oscillation taking place. But when we come to the curved condition, then there are some more forces which will be working along with the same forces which will be working on the straight section, and one of that force is the curve resistance and the centrifugal force. So, due to these centrifugal forces, or the curve resistance is being offered, the curve resistance is going to create its effect on the locomotive and its power, whereas the centrifugal force will be creating an effect on the turning of overturning of the rolling stock at that section. And therefore, there are chances that either the overturning may take place, or there are chances that depending on the speed and depending on the type of the super elevation provided or not provided, there may be a derailment of the at that section. Further, when we are talking about this curved section, what we have observed is that because of the centrifugal force, there is a tendency of the forward wheelbase to go in the outward direction, whereas because of the rigidity, the trailing wheelbase remains in the inward direction. So, in this case, what we can see is that there is a higher diameter which is coming on the outer wheel surfaces, whereas on the inner wheel surface, on the inner rails, this diameter may be a little lesser. In that case, there is an unequal distribution of load which is coming on the two rails which are laid side by side, and this unequal distribution is one case which may cause some overturning effect, because there will be a moment which will be coming because of the unequal loads on two wheel bases. Then running will also not be smooth on the curvature, because there is some resistance, and due to this resistance the running is just become a little restricted, and due to this restricted condition we feel that we are feeling a sway in one particular direction. This is what you must have observed while sitting in any vehicle or while sitting in a train, and when that train negotiates a curve. When the train is negotiating a curve, you feel that you are moving in a certain one direction. Your part of a body moves in one direction, where the other part of the body tries to remain in the same location where it was, and that is because of this curvature. So, we feel that due to this curvature, running remains not smooth. And further, when we are having the curved tracks, then more fittings are required, so that the effect of centrifugal force, due to which these rail sections may go out of section, they may go out of alignment, or they may go for gauge, they remain in its position, and so as to make them remain in that position, more fittings are needed or they are provided. Then there are certain locations where the curves are prohibited, like on bridges, in tunnels, on viaducts. We have seen in the case of bridges, when we discuss the obligatory points, that as far as possible at the sections where the bridges are being provided, there should not be a curve, these should be provided on a straight section. The reason behind is that we have to increase the size of the bridge, and which is a costly construction. Similarly, is the case in the tunnels or viaducts, because they are all very costly structures, and we have to reduce the overall cost of the alignment. Therefore, the curve should not be provided at those locations where there are tunnels or viaducts being provided. Similarly, in the case of approaches, in the case of approaches of stations, in the case of approaches of bridges, the curves should not be provided. They are, the reason behind here is the sight distance. The driver should be able to see up to a sufficient distance ahead, because the station area is an area where there is more safety concerns. There may be people who are crossing, or there may be some other things which may be happening on that station. So, therefore, the driver should be able to see or visualize what is happening ahead of him or ahead of the train. Same is the condition in the bridges. The driver should be able to see the whole approach of the bridge as well as the bridge, so that he can understand, he can visualize and make a decision regarding the safety of movement of a train over that bridge before approaching it. Then the locations like level crossings. In the case of level crossings also, if the curve is provided, then it will increase the length of the track on the level crossing section, and this is another hazardous condition. It has its safety implications, because the person who are crossing the railway track have to move longer distances and they remain for more time on the railway track. So, this is not good as for their safety. In the case of the cuttings also, deep cuttings also, the curve should not be provided, because they increases the length, and when they increases the length, the cost of cutting is much more than the cost of embankment. It has its economic consideration or a cost consideration. In the case of the station yards also, because the station yards are the location where more of the maintenance takes place, and there is a sort of a slow movement taking place in the it's a overall yard where the overall maintenance is coming up. It may be in the form of wagons, it may be for the locomotives. So, therefore, in the station yards also all the sections should be visible, because there may be shunting operations, there may be switch over from one track to the other track, and in all such conditions, like in even also in the case of the yards approaches where the trains are either moving into the yard or the wagons are coming out of the yard as the trains have been formed and they have to go to the platform for taking up the load. So, in all such conditions the curves should not be provided. Here side distance is one of the reason so as of provision of curves. Now, we come to the different elements or the design features of curves. The very first design feature of the curve is the degree of curve. This is the way by which the curves are designated. There are two ways by which the curves can be designated. One is by their curvature and another one is by their radius. In the case of the curvature, the degree of curve is the way by which it can be done, and this degree of curve can be found out by the angle which is subtended at the center of the curve by a chord of 30.5 meter or 100 feet long. What happens is that if we are providing a circular curve like this, then if we take a 30.5 meter long chord, so there is a 30.5 meter long chord here or a 100 feet long chord being taken on this along this circular curve, and then we see what is the angle being found by this point as this point on the center of the curve, that is this angle at this level, which may be termed as the degree of this curve. So, this is how it is found out, and if we go along from this point, that is the point of the center of this curve up to the curve, the center of the curve, then this is the radius of this curve, and there is a relationship between this distance or between this degree of the curve and the radius. What can be done is that this is the distance being moved, this is the angle and this is the radius. The relationship can be found out in this form. The degree divided by the overall 360 degrees by which it moves is equals to the 30.5 meters divided by the overall circumference when we move by 360 degree. So, overall circumference will be 2 pi r. So, with this one we get d is equals to 1750 divided by r, where r is the radius of the circular curve in meters. So, if we know the radius of the circular curve in meters, then by using this equation d is equals to 1750 divided by r, we can find out the degree of the curve. And similarly, if we know the degree of the curve, then we can also calculate the radius of the curve in the same using the same formula. Number of computations are there where the radius of the curve is to be used, and in that case, if the degree of the curve is being provided, we using this formula we compute first of all r and then use that value in the further equations. Now, when we talk about this circular curve, then the degree or the radius both are controlled. Here the smallest radius or the largest degree are controlled. There are two things which are controlling these things. One thing is that there is a flatter radius is there or bigger radius is there, it means it will be providing a flatter curve. Flatter curve means now there is a very less problem of loss of tractive effort, but if the radius is very less, it means a sharp curve is there. So, what is the governing feature which reduces or which restricts the radius to the lowest minimum value? Similarly, the degree of curve is there. The degree of curve is to be taken in opposite to the radius. It means we have to talk about the largest degree up to which we can go. and both of these things are going to be controlled by two things. One is the wheelbase of the vehicle and other one is the sharpness of the curve. In the case of the wheelbase of the vehicle, depending on the size of the vehicle, the wheelbase will be defined, and if there is a certain wheelbase, then it has a tendency to move smoothly by taking a turn at some angle or by taking a turn with respect to a certain radius. So, looking at that turning behavior or steering of that wheelbase smoothly without any safety hazards, then that is going to decide what should be the minimum radius of any curve. Similarly, when you talk about the sharpness of the curve, as the sharpness of the curve increases, the chances of overturning may also increase, and therefore, we have to look at that value up to which we can go without creating any further problem as far as the safety of the movement of vehicles is concerned in this case also. So, these are the two factors which decide what should be the minimum value of the radius or what should be the maximum value of the degree of the curve. Now, based on all these considerations, the maximum degree of curvature has been defined based for different gauges of the tracks. We have the broad gauge, meter gauge and the narrow gauge. In the case of the plain track, the value for broad gauge is being fixed at the maximum for 10 degrees. For meter gauge, it is 16 degrees, because here the wheelbase is reducing, and when the wheelbase is reducing, it means it has a possibility to negotiate a sharper curve. And then in the case of a narrow gauge, further the wheelbase is further reduced, the size of the locomotive has reduced, the size of the wagons has reduced. Therefore, it can go up to a higher value of the degree, and this is 40 degrees. So, these are the maximum values 10 degrees, 16 degrees and 40 degrees for all these tracks, and it results in the radius of minimum 175 meters or 109 meters or 44 meters in the case of broad gauge, meter gauge and narrow gauge respectively. Similarly, wherever there is a location from where the change in the direction of a track can be done, that is what is termed as turnout, at that location it is restricted to a value of 8 degrees in broad gauge, 15 degrees in meter gauge and 17 degrees in narrow gauge, and it transforms into a value of 218 meters of radius in broad gauge, 116 meters radius in meter gauge and 103 meter radius in narrow gauge. So, these are the values or the design features for the straight track and for the turnout track, and they are used in the various design of turnouts or the plain tracks. Now, another aspect of the curve is the Varsine. Varsine, as we find from figure in this one, this value, if this is the circular curve, then and this is a chord, then this distance is termed as Varsine. Okay. So, from the geometry of this curve, we have this distance and then we have another distance on this side. Similarly, if we take this chord, then we have this distance and we have another distance on this side. So, if we take the multiplication of these two, then they are going to be equal. This is what is the property of this circular curve. So, if we take the multiplication of this distance with this distance, or we take the multiplication of this distance with this distance, then what we are going to get is the same value. Looking at this property, we have written here is that this value is say V, and if they take this total value, then this total value is twice of the radius. So, it is this value will become 2 r minus V. So, we are multiplying V with 2 r minus V, that is this much. This is equals to half of the chord on this side and half of the chord on this side. If the length of the chord is C, then C by 2 multiplied by C by 2. Now, for very small values of V, this finally transforms into a value of V is equals to C square divided by 8 r, and this is how the Varsine of any curve can be computed if we know the chord and if we know the radius. This is one of a very important characteristic of this curve, which is used so as to identify the degree of curve in the field also. We will look at how we can do this is that here C is the chord in meters, r is the radius in meters, and if we are computing the value of V in centimeters, then it transforms into 12.5 c square divided by r. And in this case, if we compute finally the values of this d and the value of V, what we found is that the degree of curve is approximately equals to the versine in centimeters. And this is the property which is used in the field so as to find out the degree of curve. How we do this is that this is done using a chord of 11.8 meters or 62 feet. So, for that if we compute the values here, then V is 12.5 c square divided by r, putting a value of r is equals to, r is transformed into degree, and there are two values being taken at a different point of a time. In some of the cases we take 1750 or 1720, this is the minimum value, 1750 is another value which is being taken depending on in what units, up to what accuracy we are taking the values of chords, etc. So, if we take this value in the above equation and put it in this equation as a value of r, what we get is 12.5 c square d divided by 1720, and finally it transforms into a value of 1.011 d. So, V is very much approximately equals to d. So, in the field if we have any curve and we have to find out what is the degree of this curve, then what we can do is we will take a chord of 11.8 meters and we just put 11.8 meters from one side to the other side on that curve, and from the center of this chord find out the distance of the circular curve, and this value of the distance of the circular curve will define what is the degree of that curve, and this is how we can do the compute or measure the degree of curve in the field. Now, we come to the other design elements in this diagram. The design elements have been shown like this. This is a circular curve, and this point it is a straight section, at this point there is another straight section. So, this is termed as tangent point on this side and a tangent point on this side. Then this is the chord, this is the length of the circular curve, this is versine at EF. Then if you just extend this tangent on this side and extend this tangent on this side, they will meet at this point O. This is the point of intersection of the tangents, and this will make two angles. One angle is on this one, this is an external angle which is termed by phi, and the internal angle defined by 1. Here the 1 is the angle of intersection, and whereas this phi is termed as the deflection angle, because this is by angle by which the direction has been turned. So, we were coming in this direction and now we are going in this direction. So, we have taken a turn by this angle, that is why it is a deflection angle. And the values of these design elements we are looking here. The length of the curve can be computed as L, and this is pi r phi divided by 180. We can of course find out these equations using the geometry of that curve, that is not being shown here, and here we are directly we can compute the value using this one. Pi is 22 by 7, r is the radius of the curve, phi is the deflection angle, and 180 is the on the basis of the angle, it is here taken in radians. Similarly, the tangent length can be defined as r 10 phi by 2. This is another value which is required when we set the curves. The length of the long chord, which is T1 T2, it is equals to 2r sine phi by 2, where phi is the angle of intersection in degrees. Now, there are certain methods by which these curves can be set in the field. The methods are tangential offset method, long chord offset method, chord deflection method, and theodolite method. Now, we look at these methods one by one. In the case of tangential offset method, this is a curve, circular curve, and we have a tangent here like this, as we have seen in the previous diagram too. What we do is in this case is that we take a chord equals to C1, C2, C3 or C4, whatever distance we are taking of the length of the chord, that length of the chord is measured along tangent. So, When we are having C1, we reach A. When we are having C2, we will be reaching B or C or D likewise. Then at that point, we measure a value of offset which is equals to O, and this is given by C square divided by 2R, where C is the length of the chord and R is the radius of the curve. So, using this value, once we compute this value, say if instead of C we put C1, so we will get the offset which will be measured from A to this point A dash, and this is what is the value here. Similarly, if we have put the value as C2 as a chord, then we will be coming as O2B. So, this is O2B, this is B and this is termed as O2. Similarly, this is O3 or this is O4 and likewise. Another feature here is that once we have set the curve up to this point and then we found that there is an obstruction due to which the offset cannot be placed from this tangent in this direction, then what we can do is that at the last point we can draw another tangent like this, and then from this tangent again using the same formula we can put the offsets like this. So, we compute this length, for this length the offset, for this length this offset, for this length this offset, and this is how we keep on going along the curve. Now, this is another method, long chord offset method. In the case of long chord offset method, what we are doing is we are using the tangent length T1 T2, and in this tangent length T1 T2 at the center, that is D, this maximum value is always known and this is var sin V. Now, looking at this aspect, we have computed with respect to this value of V, and the formula says that this is equals to C square divided by 8R minus X square divided by 2R. So, if we look at this formula, then what happens is that we are talking about the offsets here as O1, O2, O3, that is this offset or this offset, and here we have V1, V2 and V3. So, we can compute this value of V1 from this side, V2 from this side and V3 from this side by taking the value of x in this direction. So, if we are taking the value of x in this direction, we come to this point, and at this point then we compute the value of V and we will get this point, and this is how it keeps on going. So, this is long chord offset method, and this is the center point. So, similarity will be there in the curve from in this direction, similarly in this direction. Then another method is the chord deflection method. In the chord deflection method, what we are doing is that this is a tangent which is known to us. From this tangent we find out an offset on the basis of the deflection. So, here we are computing this value as say x n minus 1 into x n, this divided by 2r plus x n square divided by 2r. So, here this value of x is the value which is being taken from this tangent point, and this is x1 value, and at this point the offset should be as computed by this equation. So, we have the x n is this one. If there is no previous chord in this case, then it is going to be 0. So, therefore, we are computing only for x n square divided by 2r, and here instead of taking the chord along the tangent length as in the first case, we are taking this chord along this one. So, it means at a distance of any value of x1 we will compute this component, and after computing this component we have found out this value. Now, with respect to this one we will be computing another component, and this is how we will be having this value. Then we extend this point in this direction and again we compute it, and this is how we keep on going further. Finally, there is a fourth method which is a theodolite method. In this theodolite method, it is dependent on the deflection angle, that is small delta n, and the computed value of the overall angle with respect to the tangent, that is delta, capital delta. And in this case, how we are going to compute is that again it works with respect to the tangent. So, we have this tangent which is moving in this direction, and then from this direction we are taking some deflection angle, and for the deflection angle we will try to ascertain the point at which the curve location will be there. So, this deflection angle will be computed previously, and once this deflection angle is being computed, first of all we will set it for that deflection angle, that is here it is being set like this is small value. So, at this one we will be having a value of x 1. So, once we have got this is 1 point. Then further we have the another deflection angle. So, where we will be having this deflection angle. So, a small deflection angle plus the previous deflection angle, the combination of these two will give the total deflection which will be there, that is this one. So, we have a deflection with respect to this one, this is this value, this is delta n plus 1, and then this is delta n, capital delta n. So, capital delta n plus 1 will give you the capital delta n plus 1 value. That is how we keep on further going, and we keep on marking the points at the point of intersection of this one and the deflected line of sight, and that is how we keep on computing the values, and this is with the way by which the curves are set in the field. This is one more method where we are trying to find out the curve by using the Versine of quartering of Versine method. Here what we do is the simple form. This is the chord T1 T2, at the center the maximum value can be equal to Versine V. Now, we join this point with T1 and join this point with T2, and again at the center of this one there will be Versine, and the value of this Versine will be equal to 1/4 of the Versine available here. So, therefore, it will be V by 4 and V by 4. So, if once we have got this point B on the basis of the quartering of the Versine, then this point B will be further connected to T1 here, and similarly it will be connected to the A, that is the previous Versine point here, and the same will be done on the other side of the curve. Now, once again we have got another chord. So, on this one we can find out the Versine, which will be 1/4 of the previous Versine, that is the previous Versine is V by 4. So, the new Versine will be V by 16, and we will get another point, and this is how we can keep on going, and whatever accuracy we want with respect to that accuracy we will go to a smallest value, and we will be having a smooth curve being drawn like this. Now, once we have completed the curves, we are coming to the next aspect, that is super elevation. Now, we define first of all the super elevation. Super elevations are also known as cant. It is the difference between the height of outer and the inner rail on a curve. By using this measurement, that whatever is the difference between the levels of the inner and the outer rail on a curve, that value is defined as super elevation. In this case, the inner rail is taken as a reference rail and is maintained at its original level, whereas with respect to this inner rail, the outer rail is raised, and it is raised by a value of equal to super elevation, and the inner rail is also known as the gradient rail. Now, the super elevation therefore is defined as the distance by which the outer rail has to be heightened, or it is to be raised with respect to inner rail, so as to reduce the effect of some components or some forces which are coming due to the curvature in the alignment. And of course, those forces or those effects which are coming due to the curvature is nothing but the centrifugal force which will be acting in the outward direction, and so as to nullify that, we are raising the outer rail with respect to the inner rail. So, what are the objectives of providing this super elevation? The objectives are to neutralize the effect of centrifugal force, as we have been discussing again and again, that these are provided due to the centrifugal force. And another aspect which we have discussed is that there is going to be unequal distribution on the two wheels or on the two rails. So, by providing of the super elevation, what we achieve is the equal distribution of wheel loads. Further, we will be providing a smooth track, and the passenger comfort will get improved. This is another objective, because the super elevation, once it is being provided, it will nullify the effect of centrifugal force which tries to take the system in the outward direction. Therefore, the jerk which will be working as soon as a wagon or the rolling stock moves from a straight section where there is no centrifugal force acting to a curved section where all of a sudden a centrifugal force start acting in the outward direction, a jerk will be felt. Now, if the super elevation is being provided, then this super elevation will nullify the effect of the centrifugal force, and therefore, the passenger will not feel any jerk when the wagon or when the rolling stock moves from a straight portion to the curved portion. So, this is another important characteristics or another objective for which the super elevation is provided. Further, because of this non-provision of the super elevation, where we are talking about the centrifugal force which is acting in the outward direction, because of the movement of the overall rolling stock in the outward direction or because of its rigidity, the relative movement of the front wheels and the trailing wheels, what happens is that there are all chances of wearing and tearing taking place at a higher level. Now, when this wearing and tearing can take place at a higher level, as soon as the super elevation is being provided, it reduces the effect of the centrifugal force or it nullifies it further finally. So, when it is being nullified, the wear and tear which is taking place because of the lateral oscillation induced by the centrifugal force will get eliminated. And when these are getting eliminated, the wear and tear which has resulted or which may have resulted because of this additional sway will not be there. So, these are some of the objectives for which the super elevation has to be provided on curved sections. Now, this is a curved track which is being shown in this diagram. This is the outer rail and this is the inner rail being provided here, and there is an additional rail which is being provided here in this one on the inner side of this inner rail, and this is known as check rail. We have discussed about the check rail before also, and what we have discussed is that because of the centrifugal force, there is a tendency that the hull of the system will be moving in this outward direction like this. So, from this side to this side. Once we have provided this check rail, then this check rail will not allow the wheels to move in this direction further, it will restrict that movement. And this is how it checks the movement in the lateral direction of the rolling stock because of certain reasons like the centrifugal force in the case of a curve. And this is how it maintains the safety, otherwise there will be derailment of the wheel at this location, whereas there will be overturning of the wheel on this side. So, or the overriding of the wheel on this side basically. So, these two phenomena which could have got induced will be eliminated as soon as the check rail is provided at this location. And what we see, this is a plan, and in this case this is the elevation where we can easily see that the inner rail has been provided at the same elevation where it is being provided on the straight section, whereas the outer rail has been raised. And for raising this outer rail, we are using additional thickness of the ballast cushion. So, the thickness of the ballast cushion is increased at this location, whereas it is the normal thickness at this position, and this is how we have achieved this slant location. Here the gauge has been maintained between this point and this point, whereas there is a difference in the elevation of this rail, and this is being defined by this value, and this value is termed as super elevation. So, in the case of super elevation, we have to look for the equilibrium condition, and there is a certain condition at which the equilibrium which the super elevation is termed as equilibrium super elevation. What happens here is that to counteract the effect of centrifugal force, the outer rail of the curve is elevated with respect to the inner rail by an amount equal to super elevation. Now, this is a state in which both the wheels exert equal pressure on the rails, and in this condition the super elevation is enough to bring the resultant of the centrifugal force and the force exerted by the weight of the vehicle which is acting at right angle to the plane of the top surface of the rails. So, this is a condition which is happening, that we are trying to achieve a state in which the resultant of the centrifugal force which is acting in the outward direction and the force, that is a vertical downward force, that is the load which is acting downwards. If we take the resultant of these two, this tries to remain within the area of the wheel sections, and if it is remaining in that area, then the chances of overturning etcetera will be omitted. So, in this situation, when we have achieved the equal load on both the rail systems and the resultant is falling within the required area, then this state of equilibrium, the super elevation, is termed as equilibrium super elevation. So, this is how the equilibrium super elevation can be defined. Here the same thing is being tried to show. Here the section is being as shown previously. This is the slanted condition where the outer rail is up and inner rail is down by a value of super elevation E, that is a small e shows this super elevation value. Here when we look at the weight component, then the weight component is acting vertically downwards like this. This is the weight component, and the centrifugal force will always act horizontally in the outward direction. So, the centrifugal force is acting horizontally in the outward direction like this. Now, the amount by which this super elevation is being provided, there is a tilting of this base by an angle alpha. So, this is the horizontal level which was previously provided, and now this is being tilted at this level. So, the angle being made by these two surfaces, this surface and this horizontal surface, is angle alpha. Therefore, when we take the resultant of this centrifugal force F and the weight W which is acting in downward direction, then this resultant will be acting likewise at an angle alpha with respect to W, and this is what is defined. So, if this is working in this form, then this remains within the wheel base condition, and this is what is the equilibrium condition being achieved in this one. And in this condition, the weight or the load which is transferred through this wheel or the load which is transferred to this wheel, they are same in nature. Now, we come to the design aspect of super elevation. How we design the value? The centrifugal force is defined as F is equals to m multiplied by a, where a is the radial acceleration and m is the mass of the body, and this radial acceleration is computed as v square divided by r. Therefore, this value of F will become F is equals to w divided by g into v square divided by r. So, this is one equation which is there, where m is being converted into this unit. Here w is the weight and g is the acceleration due to gravity. So, m is equals to w divided by g here. Further, when we are talking about, as we have seen, this is smaller angle by which it is getting tilted up, where it is being defined as alpha here. Now, in this side it is being defined as theta. So, alpha or theta, they are the same thing. When we take the angle tan of this angle theta, then it is nothing but it is super elevation divided by gauge. So, what we see is that if we are taking the tangent of this one, then it can be taken as this is the super elevation value E, super elevation divided by gauge. Gauge is taken in this direction, that is g. So, this is E divided by g is nothing but tangent of this alpha. And similarly, what the same thing we are trying to find out on this side. If we are taking that this tangent alpha, then this is nothing but the force, centrifugal force divided by the weight. So, F divided by W. So, using this geometry of this figure as well as the geometry of the or the point of application of the forces and their relative positions, we can compute the value as shown here. So, tangent tan theta is nothing but E divided by G. Similarly, tan theta is also F divided by W. Therefore, E divided by G is nothing but is equals to F divided by W. Now, in this case, the F will be equals to E into W divided by G, where G is gauge, W is the weight and E is the super elevation. Now, if we use this equation along with the previously found equation for f, what we get is E is equals to G with multiplied with mv square divided by r, or this transforms as or divide, and this is divided by m divided by g, and finally it transforms as gv square divided by gr, where g is the gauge, v is the speed of the train, small g is the acceleration due to gravity, and r is the radius, and the values have been given as v is the speed in meter per second, r is the radius in meter, and g is the acceleration in meter per second square. Now, the value of g, how this value of g is taken and what should be this value of g, we will be looking at that aspect. The value of g is here being defined as dynamic gauge, where the dynamic gauge is the gauge plus width of the rail head. So, if we take the gauge and just add to that the width of the rail head, the gauge in the case of the broad gauge is 1676 to 1676, if we add the width of the rail head, we get 1750. Similarly, in the case of meter gauge, where we are having 1000 mm, if we add the width of the rail head, we get 1058 mm, and this is the value which is to be used here as g. And if we are using the this equation where g is v square divided by 127 r, then in this case v is given as in kilometers per hour, and when we use the value of g in mm, then what we get is that we are getting the value of E in mm. We will just look at an example here. There is a broad gauge track which is provided with a 2-degree curve, and the equilibrium speed is defined as 80 kilometers per hour. For this, we have to compute the value of super elevation. Now, once we have been given the degree of the curve, then using the relationship between the degree and the radius, then we can compute the value of radius. So, the radius will be nothing but 1750 divided by d, and on the basis of this we get 875 meters. Now, super elevation, as we have seen, is computed as gv square divided by 127 r in mm, where g in the case of the broad gauge track will be 1750 mm. We have again seen this value previously. Putting the values in this equation, what we get is 1750 multiplied by, in this case the v is in kilometers per hour, so a square of 80 divided by 127 multiplied with the radius 875, and the value of E which we are getting is 100.8 mm. So, this is the amount of distance by which the level of the outer rail has to be raised with respect to the level of the inner rail, or we can say it is 10.08 centimeters. So, this much value, by this much value it is to be raised if we have to keep the speed as 80 kilometers per hour. Now, there is another way of finding out the value of the super elevation in the field. There is a thumb rule for calculating it, and this value will give the value in centimeters. In the case of broad gauge, it is given as a speed in kilometers per hour divided by 10. So, as we have seen in the previous case, the speed was 80. So, 80 divided by 10 means 8, 8 square means 64, is to be multiplied with degree of curve divided by 13. In the previous case, the degree of curve was 2. So, 2 is to be divided by 13 means it is 0.1 something. So, it is to be multiplied with this one, and we will get the value in centimeters. Whereas, and here we are taking in the case of meter gauge, the value is being taken as 3/5 of the above value. So, whatever we are computing for the broad gauge using the same this formula, we now if take the value as 3/5 of this one, then this will pertains to the meter gauge track. So, these are the thumb rules which are used by the field engineers in the field for calculating the value of super elevation while checking whether the super elevation provided at any location is right or not. Now, we come to the another aspect of super elevation. Here in this diagram, what we see is that there are is one track which is coming in this direction, and then finally there are divergence in the track. That main track is moving in this direction, but there is another branch line which is moving contrary to this direction. So, in this case, if we talk about the curve which is being provided in this section, there is a contrary condition getting created. What we found is, if we look at this curve like this, then the centrifugal force is acting in this direction, and therefore, this is the outer rail. This outer rail has to be raised with respect to this inner rail. Now, if we look at this curve, in this curve the curvature is in this direction, therefore, the centrifugal force is acting in this direction, which is opposite to the centrifugal force for the main curve, and therefore, this rail has to be raised and this rail has to be kept at the same level. Now, if we are raising this rail in this section and if we have to raise this rail in this area, then it is not feasible to do both the things simultaneously. And this is where, when we provide the super elevation for this curve, then this will act as a negative super elevation, because it is going up, whereas in this direction it has to go up in this direction. So, it acts as a negative condition for the other track, and this is how it is termed as negative super elevation. And we have to look at these values of negative super elevation and design the track or design this connectivity accordingly. We will be looking at this design, how we do this. In the case of this one, when we are having a main line and a branch line condition, here there are two ways which may happen. The first condition is that the super elevation for the branch line can be calculated. Then in this case, what we do is that first of all, we will calculate the equilibrium super elevation for the branch line, that is E, by using the formula G V square divided by 127 R. What happens is that the degree of the curve for the main line as well as for the branch track will be given to us, and using that degree we can compute the radius of both the tracks. So, we have the radius of the main track and we have the radius of the branch line. Now, once we have these values, in the case of the branch line, suppose the speed is being defined. Now, once the speed is being defined for the branch line, then we can compute the equilibrium super elevation for the branch line, whereas if the speed is being defined for the main line, then we can compute the equilibrium super elevation for the main line. Now, whatever is the condition, like in this example, we are taking the condition where the speed is being given for the branch line, and therefore, we have computed the equilibrium super elevation for branch line, that is E. Now, we find the super elevation value x, some tentative value which is defined as E minus C D, and this value C D is known as Kent deficiency, where their value of Kent deficiency has been defined for different tracks. Now, once this value is being computed for the branch line, the same value is to be provided on the main line. Now, when we go to the same value which is to be provided on the main line, what happens is it changes its sign, and instead of, say, if this value is coming as a negative value, then now when it comes to the main line, it will become a positive value, and this positive value of x will be added again to a value of C D which is permissible for the main line. And once we get this value, whatever is the summation of these two values is the super elevation which is to be provided on the main line. And with respect to this super elevation to be provided on the main line, using again the equation G V square divided by 127 R, we can compute the value of V, that is the speed by which the trains can move on this track. Now, we take up the another case where we can compute the super elevation for the main line, because the speed on the main line is given to us. Then we find out super elevation as E minus C D for the main line. Then this super elevation is to be transferred to the branch line, and here again it will change the sign. So, therefore, it will be taken as minus x, and this minus x will be added to the Kent deficiency which is permissible for the branch line, and this will give us the value of E B, and for this value of E B, then we will be finding out the permissible speed for the branch line. So, more or less the procedures remain same for both the cases as we have seen. We take the example here. We have a broad gauge track with 2° curve and a branch line with 4° curve, where the speed on the branch line is 30 kilometers per hour, and we have to find out the speed on the main track. So, we are computing the radius on the branch line using the equation 1750 divided by d, where d is 4. So, we are getting 437.5 meters, and then we compute the value of super elevation EB by GV square divided by 127 R, and we get the value EB as 28.34 mm. Now, the current efficiency defined for the branch line or the track, broad gauge track, is 75 mm. So, therefore, finding out the value of x is 28.34 minus 75, which is negative, minus 46.66 mm. Now, when it comes to the main track, then it will change its sign and it will become 46.66 mm. Now, this value of 46.66 mm will be added to the Kant deficiency for the main track, again as 75. So, it will be 121.66 mm, and then we have the radius of the main track, which is 875 meter, based on the degree of the curve of 2 degrees. We get the speed by using the formula, and we find out that this value comes out to be 87.89 kilometers per hour. So, we can say roughly around 85 kilometers per hour is the speed of the main track, which is provided with 2-degree curve. This is how we can compute the value of the negative super elevation and super elevation on the two tracks. So, we stop at this point, students. We have seen today in this lecture the two aspects. One is the horizontal curves, another one is the super elevation and its design. We will be continuing with the geometrics in the further lectures, and now I stop at this point. Say goodbye to you. Thank you.
Thank you.